For 438, we have 2,500 carbon steel balls with given properties being annealed in an oven at a certain temperature. And here we're trying to find the time it's going to take for them to cool down after leaving the oven, and then find the total heat transfer for a certain number of balls, 2,500 of them. So first we're going to find the BO number to confirm that lumped analysis can apply, which we find here. And then we're going to find the parameter b, so we can use that t of t minus t infinity over ti minus t infinity is equal to e to the negative bt, and solve for t. We find t here, it's 167 seconds for those balls to cool, and that's assuming that they're perfectly spherical and that we have these constant thermal properties. And then we can just use that q dot's going to be equal to mcp delta t, and substitute in rho v for m, multiply with the number of balls to find the total heat transfer. For 100, we're looking at the convection heat transfer from wind blowing over the Earth, and we're trying to find that the temperature of the Earth at varying x's below the surface. We're going to assume Earth is a semi-infinite medium, that the area we're looking at has in variation is far away from the other, so that applies. We're given these properties, and here we're going to use the error function relationship for this. Earth as a semi-infinite plane wall. We find the mu here, and we find that it is significantly more than 4, so this portion of the error function is going to go to 0, because the error function as of that more than 4 is going to go to 0, which simplifies, and then we can rearrange for x and find the temperatures at these various x's. This problem, there's a block of ice melting with the walls and top exposed, and we're going to treat it as 2D conduction, so we can use the product solution for a multi-dimensional object. First, we're going to find the BO numbers, so we can find properties for the top and the sides where it's going to be occurring. We're approximating those as plane walls of thickness 2L. So when we do these calculations, we're going to use A over 2 and B over 2 here. So that's a typo, that should be A over 2. So we can use that this theta function is equivalent to that of the top squared times that of the wall. And then we can use this equation for the plane wall. We can find tau, which we're going to use. I'm going to optimize in Excel to find the appropriate time, and then double check after. For this, I'll circle back on my confusions, but my solution doesn't actually confirm, which is strange, but I did find a time that satisfied this, so after 7.7 hours. Here we've got steel undergoing decarbonization, and we're going to treat this as a semi-infinite medium, so very similar to the convection of a semi-infinite medium on the Earth, except we're using DAB instead. We're going to make the same simplification because mu is, well, that's another confusion because I could not figure out how to calculate the mu, and I didn't want to make any assumptions that I couldn't make. However, I did solve it following the assumption the solution made. That's another point of confusion there. But if we assume that that's going to be more than 4, this part of the error function is going to go to 0. Then we can rearrange using concentration instead of T. And if concentration is equal to 0.4, the initial concentration, then we can use table 4.4 to find the value within the error function, rearrange for x, and then find the temperature at 1 hour and 10 hours, or the x when time equals 1 hour and 10 hours. So my 2 points of confusion are how we can confirm this error function goes to 0 here, and why up here I had difficulty confirming a tau such that this one-term analytical solution would apply.